33 billion tons. That is the lower mass limit astronomers are now assigning to our newest interstellar visitor, 3I Atlas. To grasp the scale, imagine something with a weight 40,000 times greater than the Empire State Building. And yet, despite this staggering heft, Atlas drifts silently through the cosmic dark, releasing jets of gas without producing any noticeable push on its own orbit. It's like watching a freight train propelled by birthday candles, a paradox in motion. But the mystery doesn't stop with its mass. What unsettles researchers even more is the discovery order itself. With an object this massive, logic dictates we should have spotted dozens, even hundreds, of smaller bodies long before something so monumental revealed itself. That never happened. Which means one of two things. Either our entire understanding of interstellar debris is fundamentally flawed, or Atlas represents a category of object that challenges the very rules of what moves between the stars. This isn't merely a curiosity, it could be a turning point in astronomy, one that forces us to rewrite the cosmic inventory of our galaxy's outskirts, and the implications reach far beyond science. If such a giant could slip past our telescopes until now, the natural question follows: what else is out there, still unseen, still waiting to pass through our solar neighborhood? The latest analysis makes the claim unavoidable. 3I Atlas is at least 33 billion tons in mass, with a core spanning 5 kilometers or more in diameter, orders of magnitude above the handful of fragile interstellar wanderers identified in the past. The idea of interstellar objects being lightweight fragments, brittle shards cast off from alien systems, has just been shattered. The numbers come directly from the Center for Astrophysics at Harvard, where scientists compiled an extraordinary dataset: 4,022 positional measurements gathered from 227 observatories across the globe. This isn't speculation anymore. It's preliminary, yes, but it's a hard lower bound, and it paints a picture of something colossal, something that simply shouldn't exist according to our models. For a moment, let's step back into the math. Astronomers detected virtually no measurable non-gravitational rocket push from outgassing. The upper limit sits below 15 times 10 to the power of -9 meters per second squared. And when you convert those units, you're talking about forces so minuscule, they barely rise above the background noise of measurement itself. But here's the puzzle. A weaker than expected thrust means a much larger mass, a very large mass. The rocket effect is straightforward physics. When a comet approaches the warmth of a star, its ices sublimate into gas. That gas escapes, producing jets that act like tiny thrusters, nudging the comet's orbit ever so slightly. We've witnessed this countless times. And yet, 3I Atlas breaks the pattern. It shows all the signs of activity: plumes of water vapor, carbon dioxide, even traces of exotic compounds. But the expected shove? Nowhere to be found. The only explanation that fits is mass. A staggering amount of it. Why does this matter? Because we've been here before. Oumuamua displayed odd accelerations that baffled scientists years ago, hinting at something outside the normal playbook. Then came 2I divided by Borisov, behaving like a textbook comet familiar, reassuring, almost boring in its predictability. But now, 3I Atlas changes the game. A heavyweight, active like a comet, but shrugging off its own exhaust as if it were nothing at all, like a mountain, ignoring the morning fog swirling at its base. We are staring at a regime we have never observed before. And the community has been captivated. Astronomers speak with a mix of curiosity and cautious skepticism. Coverage has echoed the same central point. The mass limits appear consistent, the data compelling. But everyone underlines the same caveat: it hasn't yet faced peer review. It's important to underline, this has not yet undergone peer review. Extraordinary claims must pass through the ordinary machinery of science, exactly as they should. And yet, the tension is unmistakable. You can almost feel the field holding its collective breath. So let's establish what we know for certain. This is only the third confirmed interstellar object ever detected. 3I Atlas was discovered on the 1st of July 2025 from facilities in Chile. The Minor Planet Center officially cataloged it as C divided by 2025 N1 Atlas. But to everyone, it's simply 3I Atlas. The designation 3I stands for Third Interstellar, a quiet reminder of just how rare these wanderers truly are. And before anyone asks about planetary defense, Earth is perfectly safe. Its closest approach will come on the 19th of December 2025, passing at a distance of roughly 1.8 astronomical units, about 170 million miles. That's closer than some asteroid flybys, yes, but still comfortably far. We are watchers here, not targets. The visuals tell their own story. On July 21, the Hubble Space Telescope captured 3I Atlas, unveiling what astronomers described as a teardrop-shaped cocoon, glowing with an unusual light from the Sunday. Most cometary tails stream away from the star, sculpted by solar wind and radiation pressure. But Atlas defied expectation. It displayed a forward-facing glow, an anti-tail that pointed directly toward our star. That phenomenon is not unprecedented, but it is rare enough to raise eyebrows. By August 27, observations from the Gemini South Telescope revealed that the anti-solar tail had grown even more pronounced. The morphology was evolving as the object warmed, painting a picture of complex dynamics, shifting dust, streams of gas, patterns of flow that defied easy explanation. Each new image became another fragment of evidence in the growing mass puzzle. And this is where the numbers clash so violently with expectation. If 3I Atlas truly harbors a 5-kilometer core and weighs in at 33 billion tons or more, then it is 3 to 5 orders of magnitude more massive than Oumuamua or 2I divided by Borisov. That's not a modest step up. That's leaping from pebbles to boulders in the supposed stream of interstellar debris. Population statistics suggest the opposite. We should first be finding smaller interstellar objects. They are easier to eject from their parent systems, vastly more numerous, and require far less energy to fling into interstellar speeds. And yet, here we are, 3 visitors in, and the latest is by far the largest. It's like discovering elephants before ever noticing the mice. The mass estimates rest heavily on assumptions, rates of outgassing, velocities of the escaping material, the physics of sublimation. That's why the James Webb Space Telescope turned its gaze toward 3I Atlas on the 6th of August 2025, providing critical spectroscopic data. Those measurements trace exactly which ices are sublimating and at what rates, feeding the models that attempt to connect visible activity with invisible mass. But models are only as good as their inputs, and right now, those inputs are still being refined. The JWST infrared spectrograph detected water ice, water vapor, carbon dioxide, and carbon monoxide. The ratio of carbon dioxide to water ranks among the highest ever measured in a comet at this distance from the Sunday. That ratio hints at an origin far from any parent star, beyond what astronomers call the carbon dioxide snowline, regions so cold that CO2 freezes side by side with water ice. The chemistry adds yet another layer to the enigma. Most comets observed at similar distances from the Sun show different volatile signatures. 3I Atlas appears enriched with compounds that demand extreme cold to condense, sketching a portrait of birth in the frozen outskirts of some distant planetary system. It carries the chemical fingerprint of alien ice. But perspective is critical. The numbers driving researchers toward the idea of a silent giant hinge on preliminary assumptions, an outgassing rate of about 150 kilograms per second, and gas velocities near 440 meters per second. These are model-dependent values, and they will be refined as more analyses are published. The JWST team has not yet released its final measurements. Even so, it's hard to argue with basic physics. If you see active gas production but detect no measurable rocket effect, then something has to give. Either the gas is not escaping efficiently, which seems unlikely, given the clearly visible coma, or the object is simply so massive that it absorbs the recoil without flinching. The evidence so far favors the second option. The visual metaphor writes itself. Imagine a person trying to move a freight train by throwing tennis balls at it. The balls bounce off. The train doesn't budge. and the onlookers suddenly realize they're dealing with something far more substantial than appearances suggested. 3I Atlas seems to be the freight train of interstellar objects, and that leads to unsettling questions. Questions about our very understanding of the galactic debris field. If massive bodies like 3I Atlas are truly out there, then where are all the smaller cousins we expected to find first? Are they invisible to current surveys, whittled away by interstellar erosion, or simply far rarer than our models predict? The stakes go well beyond academic curiosity. The upcoming Vera Rubin Observatory will scan the southern sky every few nights, with the potential to discover dozens, perhaps hundreds, of interstellar objects every year. If 3I Atlas represents the typical mass of interstellar visitors rather than an extreme outlier, then our entire framework for understanding planetary system formation will need to be rewritten. Which brings us to the crucial question: the evidence that pushed researchers toward this silent giant hypothesis, can we trust it? Part 2. The Silent Giant. The case rests on a trilogy of compelling lines of evidence. First, the upper limit on non-gravitational acceleration is so small it barely registers above zero. Second, visible cometary activity has been captured by multiple ground-based observatories and space telescopes. Third, the unusual carbon dioxide-rich chemical profile revealed by JWST, which stands out sharply when compared to solar system comets observed at similar distances from the Sunday. To understand why this matters, let's unpack the rocket effect in simple terms. Picture a garden sprinkler, spinning as jets of water spray outward from its arms. The escaping water creates tiny forces that make the sprinkler rotate. Comets work the same way. As their ices sublimate into gas, they release jets that function like miniature thrusters. The effect is small, but measurable enough to alter orbital paths over time. Astronomers have recorded these non-gravitational accelerations in hundreds of comets. Non-gravitational accelerations in comets are routine physics. They're expected, they're predictable. Astronomers have cataloged them in hundreds of solar system comets. Every time a comet swings close to the sun, sublimation ignites. Water ice, carbon dioxide, carbon monoxide, all venting into space as jets. These tiny thrusters push on the comet's nucleus, producing subtle orbital deviations that are straightforward to measure. It's part of the standard cometary toolkit. But 3I Atlas breaks that pattern completely. Despite clear evidence of outgassing water vapor streaming at hundreds of meters per second, carbon dioxide generating an enormous coma stretching across hundreds of thousands of kilometers, the expected orbital push is simply absent. The acceleration limit is pinned below 15 meters per day squared, essentially indistinguishable from pure gravitational motion. Think about that. We can see the gas, we can measure the coma, we can calculate the velocities, and yet when we look for the telltale drift, the recoil, the rocket effect, it's not there. The physics says it should be. The observations say it isn't. To see why this is so strange, let's compare Atlas with the two interstellar visitors that came before it. The first was Oumuamua, discovered in 2017. A slender, elongated object, mysterious from the very beginning. Unlike Atlas, it showed no visible cometary activity at all. No coma, no jets, no glowing halo of vapor. And yet, its trajectory revealed measurable non-gravitational acceleration. It was drifting ever so slightly, as if something was pushing on it. But what? With no visible gas, no cometary exhaust, scientists scrambled for explanations. Some proposed hydrogen outgassing, invisible to telescopes, but strong enough to impart a gentle nudge. Others suggested solar radiation pressure, pushing on an object with an unusually elongated or even pancake-like shape. More speculative voices wondered aloud about thin film structures, solar sails, even technology. The debate has never been fully resolved. To this day, Oumuamua remains an open case file, its anomaly unexplained. Then came the second visitor, 2I divided by Borisov, discovered in 2019. And Borisov was normal, comfortingly normal, like a comet out of a textbook. Its spectrum revealed water, carbon monoxide, and other familiar volatiles. Its coma and tail behaved exactly as physics predicted. Its nucleus measured roughly 1 kilometer across, and its non-gravitational acceleration matched expectations perfectly. Borisov was the reassurance the astronomical community needed. Proof that interstellar comets could behave just like our homegrown variety. A familiar traveler from afar. Which brings us back to 3I Atlas, and the reason it has captured so much attention. Atlas combines the paradoxes of both of its predecessors, yet inverts them. Where Oumuamua had acceleration but no visible activity, Atlas has abundant activity but no measurable acceleration. Where Borisov behaved like a predictable solar system-style comet, Atlas shrugs off the very physics that should govern it. Imagine this visually. Oumuamua was like watching a drifting leaf accelerate with no wind. Borisov was like watching an apple fall, exactly as gravity dictates. But Atlas? Atlas is like watching a boiling kettle produce clouds of steam that somehow fail to move the kettle even a millimeter. The steam is there, the boiling is there, the jets are there, but the recoil? Absent. And the numbers matter. The absence of a measurable push points strongly toward a much higher mass than anyone anticipated. The implication is staggering. If Atlas is truly as heavy as estimates suggest, on the order of 33 billion tons, with a 5-kilometer nucleus, then it outweighs Oumuamua and Borisov by 3 to 5 orders of magnitude. This is not a step up, it's a leap from pebbles to boulders in the cosmic debris field. That alone forces astronomers to re-examine assumptions about what kinds of objects are ejected from planetary systems and make their way across interstellar space. By all logic, smaller bodies should be more common, easier to sling out of their home systems, more numerous by nature, and requiring far less energy to reach escape velocity. Yet our third confirmed visitor appears to be a colossus, a silent giant masquerading as a comet, ignoring its own exhaust like a mountain unmoved by morning fog. The contradiction is as profound as it is puzzling. And it's why 3I Atlas is not just another interstellar curiosity. It's a challenge to our understanding of planetary formation, of interstellar dynamics, and perhaps even of the inventory of matter wandering between the stars. 3I Atlas occupies an entirely different region of parameter space. It shows the activity we expect from a comet, jets, a coma, sublimating ices, yet it refuses to obey the physics that should govern that activity. It's like watching someone swim through water without getting wet. Logically impossible unless our fundamental assumptions are wrong. The chemistry only deepens the mystery. On August 6, the JWST near-infrared spectrograph observed 3I Atlas, detecting not only the usual suspects, water, ice, and vapor, but also carbon dioxide and carbon monoxide in unusual proportions. The ratio of carbon dioxide to water ranks among the highest ever measured in a comet at this heliocentric distance. That chemical fingerprint suggests formation far out in the frozen reaches of its parent system, beyond the carbon dioxide snowline, where temperatures drop below 125 degrees Celsius. By contrast, most comets in our solar system formed closer to the sun, in regions where water ice dominates over carbon dioxide ice. That makes Atlas chemically alien. Its volatile mix tells us it was born in an environment far colder than where most of our own comets originated. It carries the icy DNA of a world we may never see, a frozen signature from the deep outskirts of another star's domain. In our solar system, water ice dominates over carbon dioxide ice, but 3I Atlas carries the frozen memory of truly extraterrestrial conditions. The SphereX infrared space telescope detected an extended carbon dioxide coma stretching hundreds of thousands of kilometers from the nucleus. This is a gas envelope far larger and richer than a casual observer might expect from visible light images. To the eye, Atlas appears as a relatively compact glowing region. But in the infrared, it reveals itself as a vast, invisible atmosphere shrouding the solid core. And here is where the physics becomes uncomfortable. Even modest outgassing rates should generate a detectable recoil. Gas escaping at hundreds of meters per second carries momentum, and the laws of conservation demand that momentum be transferred back to the parent body. A cometary nucleus, just 1 kilometer across, losing gas at typical rates, would display accelerations easily detectable with precision astrometry. Yet the evidence says otherwise. And the 4,022 positional measurements from 227 observatories around the world all converge on the same result: residuals consistent with purely gravitational motion. No measurable push, no rocket effect, nothing. Atlas is outgassing like a comet, but moving like a dead weight. The observations span from May 15 to the 23rd of September 2025, over 4 months of continuous data, capturing the exact period when cometary activity was steadily rising as 3I Atlas drew closer to the inner solar system. The math is straightforward, but the implications are startling. If you know the rate of gas production and the escape velocity of that gas, you can calculate the expected recoil acceleration. And if the acceleration actually observed falls dramatically below that prediction, then the object must be far more massive than initial estimates suggested. It's detective work, with the law of conservation of momentum as the key witness. Right now, estimates suggest that 3I Atlas is losing about 150 kilograms of mass per second through outgassing. At first glance, that number sounds modest, the weight of just 2 adult humans disappearing every single second. But in physics, it's not the raw mass that matters, it's the momentum carried away. Gas escaping at hundreds of meters per second transfers its push back onto the cometary nucleus. And momentum is cumulative. Over hours, over days, over weeks, that steady exhaust should add up, gradually nudging the body off its purely gravitational path. Even for a substantial nucleus, the push ought to be detectable, small, yes, but visible in the fine precision of astrometric measurements. Yet the orbit of Atlas remains clean, pure, gravitational to the core. More than 4,000 positional measurements from 227 observatories all trace the same story: no measurable non-gravitational acceleration. This leaves only one conclusion: if the push is missing, it's because the train is too heavy to move. 3. I Atlas is outgassing like a comet, but its mass swallows the recoil without flinching. Like a freight train being struck by a constant stream of tennis balls, the motion is there, the impacts are real, but the giant shrugs it off as if nothing happened. The fact that this recoil remains below detection thresholds points to only one possibility: extraordinary mass. Using a typical cometary density of about 500 kilograms per cubic meter, the lower limit of 33 billion tons corresponds to a nucleus at least 5 kilometers across. By the standards of interstellar visitors, that is truly enormous. For perspective, Oumuamua was likely less than 1 kilometer at its longest dimension, weighing perhaps only millions of tons. 2. I, divided by Borisov, had a nucleus about 1 kilometer wide, containing billions of tons of material. But 3I Atlas potentially outweighs both of its predecessors by factors ranging from 10 to 1,000. A genuine heavyweight in a field previously dominated by lightweights. This is not just another interstellar rock, it's a leviathan by comparison. A nucleus so massive that it redefines expectations, behaving less like a fragile shard of debris and more like a compact mountain hurtling between the stars. The estimated gas escape velocities, around 440 meters per second, come directly from spectroscopic analysis of emission line profiles. That means the numbers are anchored in hard physics. We're watching gases stream outward at supersonic speeds, yet the object itself refuses to budge. A 5-kilometer body, enriched in exotic ices, bleeding hundreds of kilograms of material every second, and still it moves with the stately indifference of a planet. When gas escapes from the nucleus of a comet, thermal motion and bulk flow combine to broaden spectral lines in distinctive ways. By modeling these line shapes, astronomers can estimate the velocity of the escaping material, though the process inevitably involves assumptions about gas temperature distributions and outflow dynamics. The results for 3I Atlas are not unusual in isolation. The escape velocities derived on the order of a few hundred meters per second fall well within the normal range for comets. Solar system comets routinely show similar numbers, driven by the sublimation energy of their ices and the weak gravity of their small nuclei. What is unusual, what borders on paradox, is the disconnect. A comet showing abundant gas production, yet producing minimal orbital response. The exhaust is there. The mass loss is measurable. The physics of momentum transfer is unavoidable. And still, the trajectory clings to pure gravitational motion. A visualization helps clarify the strangeness. Imagine plotting comet mass versus non-gravitational acceleration for all known solar system comets. They cluster along a predictable relationship. More mass, less recoil. Smaller nuclei, more measurable acceleration. It's a tidy physical trend line. But 3I Atlas does not land on that curve. It sits far away, off the chart, in a region of parameter space where nothing should exist, massive yet unresponsive, active yet motionless. A comet that behaves like an inert asteroid while surrounding itself in a living, breathing coma. In general, greater mass correlates with weaker acceleration for any given level of cometary activity. That's the rule of thumb astronomers expect. Oumuamua sits off to one side of the chart, showing high acceleration with no visible gas production. 2I divided by Borisov falls neatly on the main trend line, behaving exactly as a comet of its size and activity should. But 3I Atlas? It occupies an empty quadrant of parameter space, a region no comet was supposed to inhabit. It combines immense mass with vanishingly small acceleration in a way that stretches the limits of physical intuition. It behaves like a massive object that just happens to be sublimating ice, rather than an icy body that is incidentally massive. The analogy writes itself. It looks like a comet, it breathes like a comet, but it shrugs off its own breath like a boulder ignoring the wind. This disconnection between appearance and dynamics forces uncomfortable questions about what we're truly observing. Could the gas production estimates be wrong? Possibly. But JWST spectroscopy places hard constraints on outflow rates, and those constraints don't leave much room for error. Could the acceleration measurements themselves be systematically biased? Again, unlikely. The orbit has been tracked by a global network of 227 observatories, with over 4,000 positional measurements carefully analyzed for errors. The consistency across that dataset strongly argues against observational bias, which leaves the most unsettling option. The anomaly is real. Atlas is exactly what it appears to be, a colossal, ice-rich traveler behaving in ways no comet should. Could the physics of momentum simply fail? Could conservation laws somehow suspend themselves in deep space? Absolutely not. That leaves mass as the only plausible explanation. 3I Atlas appears to be genuinely, anomalously massive. A silent giant, disguised as an ordinary comet, its true nature revealed only through measurements of extraordinary precision. But who gathered data fine enough to catch such tiny effects? Part 3. The Global Network of Eyes. The story of 3I Atlas has been written not by a single observatory, but by the collective vision of Earth itself. Hundreds of telescopes spread across continents, all converging on one wandering point of light. When Avi Loeb, Andrea Cloutier, and Robert Warwick compiled their analysis, they drew upon a staggering dataset. 4,022 individual measurements contributed by 227 observatories, spanning from May 15 to the 23rd of September 2025. It was one of the most comprehensive follow-up campaigns ever assembled for an interstellar visitor. At its core was astrometry, the precise measurement of celestial positions. Each telescope that turned its gaze on 3I Atlas recorded its location in right ascension and declination, the celestial equivalents of longitude and latitude. Minute shifts in these coordinates, tracked night after night, reveal whether an object moves in perfect obedience to gravity or whether subtle, non-gravitational forces are at play. In the case of Atlas, the results were unambiguous. The data lined up with pure Newtonian motion, a gravitational arc unmarred by any detectable rocket effect. If the comet was venting like a chimney, the orbit refused to acknowledge it. These measurements, precise to fractions of an arcsecond, combined to create a detailed map of the object's motion against the fixed backdrop of the starfield. Think of it as cosmic detective work. Each positional measurement is a single snapshot, one frame in a long exposure photograph of orbital motion. String enough of those frames together, and patterns emerge. Deviations from a purely gravitational trajectory reveal themselves as systematic residuals, the difference between where the object actually appears and where gravity alone predicts it should be. In the case of 3I Atlas, the residuals are vanishingly small, indistinguishable from the clean arc of gravitational motion. The precision required to detect the upper limit on Atlas's non-gravitational acceleration is staggering. We're talking about shifts smaller than 28 thousandths of an arcsecond. To put that into perspective, it's like detecting the width of a single human hair seen from 20 kilometers away. And yet, Earth's ground-based telescopes achieve this routinely, thanks to careful calibration, meticulous error correction, and the statistical power of many overlapping measurements. By pooling thousands of data points across a global network, astronomers can resolve movements so subtle they would otherwise drown in noise. It is this collective precision, this worldwide choreography of instruments, that allowed scientists to glimpse the silent weight of 3I Atlas, hidden beneath its glowing coma. So how does all of this translate into physical limits on acceleration? The relationship comes down to orbital mechanics and geometry. But the underlying physics is straightforward. Even the tiniest accelerations accumulate over time. The displacement grows quadratically with time proportional to half times acceleration times time squared. Which means that after months of observation, even the faintest non-gravitational forces should produce measurable orbital deviations. From this logic emerges the upper limit, 15 meters per day squared. The units sound awkward, but convert them into more familiar terms, and you get roughly 2 billionths of a meter per second squared. That is extraordinarily small, about 1/10,000,000th of the acceleration you'd feel in a smoothly moving elevator. In human terms, imperceptible. In cosmic terms, astonishing. Detecting, or in this case, ruling out accelerations of that scale, requires nothing less than a detective story in physics. Thousands of pinpricks of starlight measured, cataloged, and stitched into a coherent orbital arc. Each data point like a fingerprint, faint on its own, but powerful in aggregate. The result is not just a map of motion, it is a fundamental test of physics itself. A demonstration that conservation of momentum is alive, well, and whispering through the trajectories of distant comets. And in the case of 3I Atlas, that whisper is drowned out by mass so great that recoil becomes undetectable. Each observatory contributed not just its instruments, but also its unique geography and vantage point. Northern Hemisphere sites tracked 3I Atlas through the summer months, while southern facilities took over as Earth's rotation brought different regions of sky into view. It was a choreography of science across the planet, a relay race of precision. The discovery timeline itself reads like a modern astronomical thriller. On the 1st of July 2025, the Atlas project in Chile first spotted the object. At the time, it was initially catalogued as a potential asteroid. Nothing unusual, just another faint traveler against the starry background. But soon came the recovery images, archival photographs taken before the official discovery. These hidden frames, buried in older data, helped refine the orbital solution and confirmed what the initial trajectory hinted at. This was no ordinary body. The path was unbound, hyperbolic, cutting through the solar system from beyond. Within weeks, the Minor Planet Center reclassified the object as humanity's third confirmed interstellar visitor. Even the still commissioning Vera Rubin Observatory joined the effort, contributing early images that not only captured levels of activity, but also provided precise astrometry. Rubin's involvement was a preview of what's to come, the dawn of the survey era in astronomy, when telescopes will scan the entire southern sky every few nights. Once fully operational, Rubin could uncover dozens, perhaps hundreds, of interstellar objects each year, transforming these rare cosmic visitors from curiosities into a cataloged population. 3I Atlas stands as a prototype for the coming revolution in transient discovery. With sub-arcsecond precision, astronomers gain the power to rule out non-gravitational pushes that would be obvious in smaller, less precisely tracked comets. When you can measure positions to the milliarc-second level and track an object for months, even the most delicate deviations from Newtonian mechanics become detectable. This level of precision transforms asteroids and comets from faint, blurry points of light into high-resolution orbital maps. Instead of vague streaks across the sky, they become well-defined trajectories, testbeds for fundamental physics. And it isn't only the large professional facilities driving this effort. Amateur and professional amateur collaborations contributed as well. Early morphology studies and time series photometry, uploaded into global databases, added critical temporal coverage. While each individual observation might be less precise than a flagship observatory's data, together they filled the gaps, helping to document how Atlas's brightness and appearance evolved as it warmed on approach to the Sunday. In this way, the discovery of Atlas became a planet-wide collaboration. Giant telescopes charted the orbit with micrometric precision, while smaller instruments filled in the story of its changing face. Both threads woven together created the narrative, a comet-like visitor that refused to act like any comet we had seen before. The global coordination required for a campaign like this showcases modern astronomy at its most collaborative. Observatories in different time zones maintained continuous coverage, handing the baton from east to west as Earth's rotation carried each site into darkness. Radio networks synchronized schedules. Data streamed into the Minor Planet Center, where analysts compiled measurements into ever more refined orbital solutions. What makes this particularly remarkable is the speed of the process. In historical astronomy, discoveries could take months, sometimes years, to confirm and characterize. But with 3I Atlas, the progression from initial detection to detailed orbital characterization happened in a matter of weeks. The difference is the machinery of modern science: powerful computing, automated detection algorithms, and rapid global communication networks. Together, they compress discovery timelines that once stretched across entire seasons into timeframes measured in days. This is astronomy reimagined. For the 21st century, an international, digitally synchronized pursuit where the moment a cosmic visitor enters our skies, the planet itself becomes one vast, interconnected observatory. The measurement precision achieved by this global network explains how researchers could impose such strict limits on non-gravitational acceleration. When you have thousands of positional measurements recorded to millisecond precision across months of observation, even the smallest systematic deviations from a purely gravitational trajectory become statistically significant. But precision always comes with caveats, and scientists are careful to emphasize them. These are not direct mass measurements. What the data provide are residual positional limits, constraints on how far the observed trajectory can drift from the path dictated by gravity alone. From those limits, astronomers don't weigh Atlas directly. Instead, they restrict the acceleration parameter. That parameter, when combined with gas flow models, produces the controversial estimates of mass. In other words, the telescope data tell us how much acceleration is missing, and the physics of sublimation translates that absence into implied mass. But the connection is fragile. The relationship between observed acceleration limits and inferred mass depends heavily on assumptions. The rates of gas production, the escape velocities of that gas, the efficiency of momentum transfer between outflowing molecules and the nucleus itself. Change those assumptions, and the mass estimates shift accordingly. Which is why, even amid the excitement, the community holds back. The numbers suggest a giant, but whether Atlas truly outweighs its predecessors by factors of hundreds or thousands depends on models that are still being tested. The Global Telescope Network delivers positional measurements of extraordinary precision, but translating those measurements into physical properties requires theoretical modeling. Even so, the achievement deserves recognition. Detecting limits on acceleration this small pushes ground-based astrometry to its practical limits. In effect, the global network of observatories has transformed Earth into a single planet-sized telescope, with baselines stretching across continents. Each observatory contributes its unique perspective and measurement capabilities, to a collective effort far greater than what any single facility could achieve alone. The quality of these data enables tests of physics that would have been impossible just a few decades ago. When positional measurements become precise enough to constrain accelerations down to billionths of a meter per second squared, comets and asteroids are no longer just passive gravitational test masses. They become laboratories, places to study momentum conservation, the dynamics of outgassing, and the delicate interplay between thermal physics and orbital mechanics. Through this lens, 3I Atlas is more than a curiosity. It is a proving ground, a natural experiment at interstellar scales, revealing the subtle tensions between theory and observation. This level of observational sophistication explains how researchers could make such strong claims about the anomalous nature of 3I Atlas. The measurements constraining its non-gravitational acceleration rank among the most precise ever achieved for any object, whether in the solar system or beyond. And when the data reach this level of precision, unexpected results demand serious theoretical attention. The global network of eyes tracking Atlas represents not just a case study, but a glimpse of astronomy's future. Coordinated surveys, rapid response capabilities, and high-precision astrometry are poised to become routine tools not only for studying interstellar visitors, but also for monitoring near-Earth objects, tracking potentially hazardous asteroids, and probing the evolving dynamics of our own solar system. But the images captured by this worldwide campaign revealed something even more puzzling than a missing orbital push, a tale that seemed to point the wrong way. Part 4. The Coma Paradox. The Hubble image of July 21 stopped astronomers in their tracks. Instead of the classic cometary appearance, a bright nucleus trailing a dust tail swept away from the Sun, 3I Atlas showed something very different. Observers described it as a teardrop-shaped cocoon, wrapped in an unusual forward-facing glow, a sunward antitail that defied basic intuition about how cometary debris should behave in interplanetary space. Normally, comet tails point away from the Sun, swept outward by the relentless push of the solar wind and photon radiation pressure. This is one of the most reliable visual rules in astronomy. So reliable that ancient Chinese astronomers used comet tails as celestial compasses, aligning them with the heavens to track directions and omens. So when you see a comet's glow pointing toward our star, your brain goes into overdrive, struggling to reconcile the image with fundamental physics. Something doesn't add up. Antitails are not entirely unprecedented within our own solar system, but they are rare, unusual, and always raise questions about geometry, dust dynamics, and the subtle forces sculpting a comet's shroud. That's why seeing one on a massive interstellar visitor like Atlas sent shockwaves through the astronomical community. They can arise from geometry. When Earth's orbital position aligns just right, it can create the illusion of material pointing toward the Sunday. Another explanation lies in the unusual dynamics of dust grains, larger particles following ballistic trajectories that diverge from the fine dust swept away by radiation pressure. But the persistence and prominence of 3I Atlas's forward-facing glow made it strikingly unusual. This wasn't a fleeting illusion or a faint detail. It was bold, dramatic, and impossible to ignore. Recent modeling papers explain the phenomenon through a mix of grain sublimation physics and viewing perspective. As ice-rich dust particles escape from the nucleus, they continue to sublimate even as they drift outward. Under specific conditions, this ongoing release can generate sunward features when observed from particular viewing angles. The math checks out. The equations of dust dynamics and sublimation can reproduce the effect on paper, but the visual impact remains startling, especially for observers accustomed to the conventional morphology of comets. To see a comet's glow turn toward the Sun feels like watching the laws of nature bend before your eyes, even when physics provides a neat explanation. The sunward glow of 3I Atlas persisted through July and August of 2025, as telescopes around the globe tracked its evolution. This was no fleeting geometric illusion, vanishing as viewing conditions changed. The forward-facing feature remained prominent in multiple observations from different observatories, pointing toward genuine physical processes rather than a simple trick of perspective. By August 27, new data from the Gemini South Telescope revealed additional complexity. Alongside the unusual forward glow, a more traditional anti-solar tail began to emerge. Atlas's morphology was evolving in real time as the object heated on its approach to perihelion. The earliest images showed primarily forward scattering, a cocoon of light leaning toward the sunday. Later observations developed into the classic dual structure, material streaming both toward and away from the star, a comet with two personalities written in dust and vapor. Atlas was not static. It was transforming before our eyes, its appearance reshaped by physics at once familiar and alien, a reminder that even well-understood processes can take on strange new forms in an interstellar context. This evolving appearance is more than a curiosity, it matters, because the relationship between dust and gas, the lifetimes of grains, and the patterns of jetting columns all influence how bright a comet appears and where its photometric center falls. The glow we measure is not always anchored to the nucleus itself. Instead, astrometric positions track the center of light, a weighted average shaped by the distribution of dust and gas in the coma. If that structure changes systematically, the photometric center can drift away from the physical nucleus. This creates a subtle but serious challenge. Systematic changes in coma morphology could potentially bias orbital solutions used to set limits on non-gravitational acceleration. The task is to separate genuine orbital dynamics from photometric artifacts. If 3I Atlas's unusual morphology systematically shifts the apparent position of its light center, it could mimic or conceal real non-gravitational forces. Careful analysis is essential to avoid drawing the wrong conclusions about the object's mass and dynamics. Anti-tails in solar system comets are typically understood within a well-established physical framework: dust size distributions, radiation pressure, and geometry. But the early prominence and persistence of 3I Atlas's sunward glow push us into less familiar territory. Here, the ordinary meets the extraordinary, and the familiar logic of cometary physics is stretched into something stranger. The modeling community is working actively to determine whether standard dust dynamics and viewing geometry can fully explain the observations, or whether more exotic processes might be involved. The chemistry adds yet another layer of complexity to the morphological puzzle. The JWST detected a rich outflow of carbon dioxide, while spectroscopy from the Very Large Telescope revealed emission lines of cyanogen and nickel, notably without corresponding features of iron. This combination enhanced CO2, nickel without iron, and unusual coma morphology paints a chemical portrait that doesn't match the familiar templates of solar system comets. Nickel emissions themselves are not unprecedented. They have been seen before in cometary spectra, but seeing nickel lines without the usual iron companions raises questions about the underlying physics. In most astrophysical contexts, these metals appear together because they arise from similar nucleosynthetic processes and are often found in comparable chemical environments. Their separation in Atlas hints at conditions or histories we don't yet fully understand. It is as if the comet carries a chemical accent from another world, one that doesn't quite align with the dialect spoken by the comets of our own system. The selective appearance of nickel suggests either unusual formation conditions or exotic release mechanisms. These chemical anomalies may be tied directly to the morphological oddities linked through dust grain composition and sublimation dynamics. If 3I Atlas contains unusual metallic minerals or complex organic compounds, their differential sublimation could generate dust populations with distinct optical properties and dynamic behaviors, quite unlike the debris of typical comets. In this way, chemistry and morphology become inseparable. The elements Atlas carries may dictate the strange forms its coma reveals. For the general public, visual explanations help demystify the anti-tail phenomenon. Imagine animated vectors showing the sun's direction versus the tail's orientation, with perspective effects demonstrating how a shift in viewing angle can make the relationship between source and debris path appear inverted. After all, when you are watching a three-dimensional process from a single fixed viewpoint, geometry can weave optical illusions that challenge physical intuition. What looks impossible may, under the math, be nothing more than a trick of perspective. But in Atlas's case, the persistence of the anomaly hints at something deeper. The sunward glow may result from forward scattering by dust grains with specific size distributions and compositions. When particles preferentially scatter sunlight forward toward the observer rather than away from the sun, they can create enhancements in brightness that seem, at first glance, to violate the basic physics of comets. The effect is real, but its interpretation requires careful consideration of scattering theory and particle properties. Anti-tails have appeared in solar system comets for decades without revolutionizing our understanding of dust dynamics. Their presence does not automatically rewrite physics, and yet caution is justified here. The prominence and persistence of the forward glow in 3I Atlas may point to unusually strong activity levels or to dust with uncommon properties rather than to fundamentally new laws of nature. But these details matter. The balance of dust and gas shapes not only what we see, the evolving morphology and brightness of the coma, but also what we calculate. Dust dynamics feed directly into momentum transfer models, which in turn underpin the controversial mass estimates for Atlas. In other words, how the comet looks is not just an optical curiosity. Its morphology and scattering behavior influence the very equations used to weigh it. If the glow is misleading, the numbers may be too. If 3I Atlas produces more dust relative to gas than typical comets, or if its dust grains have different size distributions or compositions, then the usual relationship between visible activity and expected non-gravitational acceleration could be disrupted. What we see might no longer match what the physics predicts. Understanding this balance requires weaving together observations across multiple wavelengths and techniques. Visible light images reveal dust scattering and coma morphology. Infrared spectroscopy maps gas emissions and thermal properties. Radio observations can sometimes detect molecular transitions, tracing gas production rates directly. Only by synthesizing these diverse datasets into coherent physical models can astronomers hope to solve the puzzle. It's not a single telescope that cracks the mystery, but the combined vision of many instruments, each looking with a different set of eyes. The evolving morphology, documented by Hubble, Gemini, and other facilities, provides a time series of critical snapshots. Each image is a frame in a cosmic film reel, recording how Atlas changes as it approaches the Sunday. And with every new frame, theorists test their dynamic models against reality. Dust, gas, and light woven into equations that must either fit or fracture. 3I Atlas, in this sense, is not just an interstellar visitor. It is an experiment running in real time, challenging astronomers to keep pace with its shifting face and elusive physics. The time series data are crucial for testing dynamic models. As 3I Atlas warmed on its approach to the Sun, different volatile species began sublimating at different rates. Water ice activates around 3 astronomical units. From the Sunday, carbon dioxide becomes active at much greater distances, and more exotic ices each sublimate at their own characteristic temperatures. This chemical evolution should correlate directly with morphological changes, as different gases drive different modes of dust, drag, and jet activity. A comet's appearance is, in essence, a chemical clock. The mix of volatiles escaping from its nucleus sculpts its coma in real time. The fact that 3I Atlas continued to evolve visibly throughout the observation period suggests that sublimation processes were indeed responding to changing thermal conditions as orbital geometry drew it closer to solar heating. Its coma wasn't static, it was alive, reshaping itself under the tug of sunlight. The visual metaphor that captures this paradox is both simple and disturbing. It looks as if it's snowing toward the Sunday. Your brain recoils at the image because it violates everyday intuition. Debris should always stream away from a source of heat and radiation, not back into it. And yet, Atlas presents exactly that illusion, forcing physics to confront perception. When a comet's features seem to point toward the sun, it forces us to question our most fundamental assumptions about how matter behaves in the space environment. The coma paradox is emblematic of how 3I Atlas appears, determined to violate expectations at every level. From its anomalous mass, to its peculiar chemistry, to its backward-facing tail, each new observation adds complexity rather than clarity to the emerging portrait of this interstellar visitor. But if Atlas truly is as massive as preliminary estimates suggest, it raises perhaps the most uncomfortable question of all. Where are all the smaller interstellar objects we should have found first? Part 5. The uncomfortable implication. Population statistics create a puzzle that keeps astronomers awake at night. If 3I Atlas really weighs 33 billion tons or more, with a nucleus spanning at least 5 kilometers, then it is such an extreme outlier that our basic assumptions about interstellar demographics may need to be fundamentally revised. Logically, we should have encountered dozens, even hundreds, of smaller visitors long before stumbling upon a specimen this enormous. Think about the natural order of things. Planetary systems expel debris through a variety of mechanisms. Gravitational scattering during the chaotic early phases of planet formation. Collisions that shatter icy bodies and fling fragments into interstellar space. Migrating giant planets acting like slingshots, ejecting rubble into the galactic sea. By every model, the smaller the fragment, the more easily it should escape, and the more numerous such fragments should be. The population curve should be bottom-heavy, dominated by pebbles, shards, and icy kilometer-scale nuclei, not by giants like Atlas. And yet, here we are. 3 interstellar visitors confirmed, and the third may be the largest by far. During planet formation, through stellar flybys that disturb the outer reaches of planetary systems, or through instabilities in the debris disks surrounding young stars. In every plausible scenario, the smaller bodies are expelled more easily than the larger ones. Lighter fragments need less energy to be hurled into interstellar space, making them inherently more numerous in the galactic medium. Detection biases should reinforce this trend. Within certain size ranges, smaller interstellar objects ought to be easier to catch. While the tiniest fragments may slip beneath the limits of our surveys, objects in the range of hundreds of meters to kilometers should reveal themselves when they pass through the inner solar system, developing visible comae under solar heating. And yet, the record tells a different story. Our first 3 interstellar visitors span a staggering range of masses, from the millions of tons of Oumuamua to the tens of billions potentially locked inside 3I Atlas. The progression defies naive statistical expectations. Could this simply be a matter of selection effects? Perhaps. Wide-field surveys like Atlas and the Catalina Sky Survey have only recently achieved the sensitivity and sky coverage needed to routinely catch such fleeting visitors. The narrative of scarcity may be nothing more than an artifact of our own limited vision. Or it could mean something stranger, that what we've seen so far is not a representative sample of a hidden population, but a clue that the cosmos does not scatter its debris in the way we assume. That our 3 chance encounters are pointing instead to a deeper truth. The Vera Rubin Observatory, poised to revolutionize time-domain astronomy, is only just beginning operations, which means we may be severely undersampling the true population of interstellar visitors, catching only the visible tip of a much larger iceberg. The order in which these objects have been detected might reflect geometric coincidence more than intrinsic rarity. 3. I Atlas happened to enter the inner solar system along a trajectory almost aligned with the ecliptic plane, making it far easier to spot and track than an object arriving on a steeply inclined orbit. Its favorable geometry may have compensated for what should otherwise have been a very low probability of detection for something so massive. Alternatively, the anomaly may hint at a deeper gap in our understanding of ejection mechanisms. Perhaps certain stellar environments preferentially launch larger bodies into interstellar space. Or perhaps the smaller fragments that ought to be common are simply less likely to survive the long, hostile journey between the stars. The idea of fragility deserves serious attention. Cosmic ray bombardment, collisions with interstellar dust, or sublimation triggered by casual stellar encounters could erase smaller debris from the observable population. Objects just a few hundred meters across might not endure millions of years adrift in the galactic medium. In that case, what reaches us would naturally be biased survivors, selected not by chance, but by resilience. The weaklings reduced to cosmic dust, while only the most robust giants endure to wander across solar systems like ours. But even after accounting for these survival effects, 3I Atlas remains statistically awkward. Population synthesis models the same kinds that successfully explain the demographics of the asteroid belt and the structure of the Kuiper belt struggle to accommodate such a massive interstellar visitor appearing so early in our discovery. Timeline. Either the models require updating, or Atlas is exactly what it seems, a truly rare event, one that just happened to occur during humanity's very first serious attempts to study interstellar objects. The historical context sharpens the puzzle. The discovery of Oumuamua in 2017 marked the dawn of interstellar astronomy. 2I divided by Borisov followed in 2019, showing us that at least some visitors behave like the familiar comets of our own solar system. Now, in 2025, 3I Atlas expands that record to 3 hardly enough to draw broad conclusions about galactic populations. We are essentially trying to map the demographics of an entire galaxy's worth of debris from just 3 data points. It is like attempting to chart the distribution of human heights after measuring only 3 randomly chosen individuals. With such a tiny sample size, a single outlier can distort the statistics beyond recognition. And yet, hope lies on the horizon. The Legacy Survey of Space and Time at the Vera Rubin Observatory will scan the entire southern sky every few nights for a decade. If predictions hold, it could uncover hundreds, even thousands, of interstellar objects, transforming today's trickle of anomalies into tomorrow's dataset. Atlas may be a rare giant, or the first messenger of a hidden population waiting to be revealed. If 3I Atlas represents the typical mass of an interstellar visitor, then the Vera Rubin Observatory should detect giants like it on a regular basis. If instead it is merely a statistical fluke, Rubin's survey will soon flood the discovery lists with smaller, more ordinary specimens. What's at stake goes far beyond academic curiosity about interstellar demographics. If massive objects like Atlas are common products of planetary systems, then our models of planet formation must be revised to explain how such enormous bodies are efficiently ejected into the galactic sea. Current theories emphasize planetary migration and gravitational scattering during the chaotic early phases of system evolution processes that generally favor the expulsion of smaller debris, not colossi. On the other hand, if Atlas truly is anomalous, then its unusual properties may point to exotic formation pathways or rare survival strategies that allowed it to grow to unprecedented size before its expulsion. Understanding these processes could shed new light on aspects of planetary system evolution that remain obscure even in our own solar neighborhood. This is where the puzzle cuts to the heart of galactic astrophysics. Stars are born in clusters and loose associations, where close gravitational encounters between systems can scatter debris across interstellar space. The efficiency of those dispersal events, combined with the galaxy's star formation rate over cosmic time, determines how many interstellar objects should be drifting through the void at any given moment. Atlas is more than an interloper. It is a data point with the potential to validate or unravel our models of galactic debris. Its true nature, typical or anomalous, will shape how we understand not just comets, but the hidden architecture of planetary systems across the Milky Way. Current estimates suggest that the local interstellar medium contains billions of objects larger than 100 meters. Most remain invisible, unless they pass close enough to the sun to grow a detectable coma or reflect enough sunlight to be seen directly. The real challenge lies in bridging the gap between theoretical populations and the tiny handful of objects actually observed. Telling this story responsibly means acknowledging what we don't yet know, while keeping alive the excitement of what might soon be uncovered. The mass estimates for 3I Atlas could prove to be off. The population statistics could reflect nothing more than observational biases, rather than genuine anomalies. The uncomfortable implications could dissolve as more data accumulate and theoretical models sharpen. But that uncertainty makes the story more compelling, not less. What we are watching is astronomy confronted with truly surprising observations, evidence that doesn't fit neatly into established frameworks. Whether Atlas proves typical or exceptional, it forces the field to confront fundamental questions. How does matter move between stellar systems? What does that motion reveal about the galaxy's evolution? The sample size problem will not remain unsolved forever. As surveys improve and discovery rates rise, the trickle will become a stream. Within a decade, we may have dozens, even hundreds, of interstellar visitors to study, each one a clue, each one sharpening the statistical picture that today rests on only 3 fragile data points. Population statistics will one day shift from speculation to robust inference, grounded in meaningful sample sizes. Until then, 3I Atlas stands as a puzzling ambassador from the space between stars, carrying information about conditions and processes in stellar environments we can barely imagine. Its anomalous properties, whether real or only apparent, serve as a catalyst, driving better observations, sharper models, and deeper questions about our place in the cosmic ecosystem. But the uncomfortable implication remains. If we are encountering massive interstellar objects before the smaller ones, then something critical is missing in our understanding of how debris moves through the galaxy. The question is whether that missing piece reflects observational bias, theoretical blind spots, or genuinely exotic physics operating in the vast gulfs between stellar systems. Before we can resolve the demographics, we must first confront the predictions themselves. What do current ejection and reservoir models really say about visitors like 3I Atlas? Part 6. The Interstellar Reservoir Problem. The galaxy itself functions as a vast redistribution network for planetary debris, with stellar systems continuously ejecting material that becomes the raw supply for interstellar wanderers. Each star contributes its fragments to the galactic commons, seeding the void with remnants of formation and destruction alike. Understanding this cosmic recycling process requires modeling 3 main channels of ejection: planetary scattering, close stellar flybys, and instabilities in protoplanetary disks around young stars. Of these, planetary scattering dominates current theoretical frameworks. During the chaotic early phases of planetary system evolution, massive bodies migrate through gravitational interactions that can hurl smaller objects onto hyperbolic escape trajectories. The process is often compared to a game of cosmic billiards. Planets act as cue balls, striking asteroids and comets hard enough to send them flying into interstellar space. But here lies the catch. The physics favors lighter projectiles. In this scenario, the velocity imparted scales inversely with the object's mass. In simple terms, smaller fragments reach escape speed more easily than heavyweight specimens. A Jupiter-class planet can readily eject kilometer-scale comets from its system. But to launch something the size of 3I Atlas, a potential 5-kilometer-wide, multi-billion-ton colossus, requires much more specific geometry and far more efficient energy transfer. In other words, giants should be the exception, not the rule. And yet, one of the very first interstellar objects we encounter may be exactly that, a heavyweight that defies the statistics. Stellar flybys offer an alternative mechanism for ejection, one that may be especially important in young stellar clusters where stars are born in close proximity. When another star passes within a few hundred astronomical units of a planetary system, its gravitational pull can destabilize the outer reservoirs of comets and planetesimals, scattering them onto escape trajectories. The efficiency of this process depends on several factors: the relative velocity of the flyby, the minimum distance of closest approach, and the architecture of the target system's outer regions. But unlike planet-to-planet scattering, stellar encounters operate on a far greater scale. Because stellar masses exceed planetary masses by factors of hundreds to thousands, a close passage by a massive star could in principle eject bodies weighing billions or even tens of billions of tons. That makes flybys a plausible mechanism for producing interstellar behemoths like 3I Atlas objects so massive that ordinary planetary dynamics would struggle to explain their escape. The third major pathway is disk instability during the earliest phases of system formation. In young, gas-rich disks, turbulent interactions and gravitational instabilities can disrupt the trajectories of newly forming planetesimals. Some are swallowed by growing planets, some spiral into their host star, and some are flung outward with enough momentum to leave the system altogether. Together, these three processes, planetary scattering, stellar flybys, and disk instabilities, constitute the great engines of galactic redistribution, the mechanisms that populate the interstellar medium with wandering debris. Before planets fully form, gravitational instabilities in protoplanetary disks can generate spiral density waves and other non-axisymmetric structures capable of scattering embedded planetesimals. This process operates during the first few million years of stellar evolution, when disks still hold a significant fraction of their mass in gas and dust. The challenge lies in predicting which ejection mechanism dominates under different stellar environments and how the resulting size distributions compare with observations: young stellar clusters versus field stars, metal-rich systems versus metal-poor ones, binaries versus solitary stars. Each environment likely produces its own signature of ejection and debris characteristics. Observational constraints, however, remain frustratingly scarce. With only Oumuamua, 2I divided by Borisov, and 3I Atlas confirmed so far, the uncertainties in population demographics span orders of magnitude. Statistical inference becomes almost meaningless when outliers can completely dominate the sample. It is like trying to deduce the rules of a vast game by watching only 3 unpredictable moves. Each one could be typical, or each could be an exception. And until more interstellar objects are found, the line between pattern and coincidence remains blurred. The commissioning phase of the Vera Rubin Observatory has already provided the first glimpses of 3I Atlas, a preview of the revolution to come in interstellar object astronomy. With its wide-field camera and rapid cadence survey, Rubin will be capable of detecting dozens, perhaps hundreds of interstellar visitors every year, transforming population statistics from speculation into robust empirical science within the next decade. Current reservoir models attempt to connect ejection processes with the observed characteristics of interstellar visitors by modeling the accumulation of debris across galactic timescales. Stellar formation rates, the dynamics of stellar clusters, and the architectures of planetary systems all contribute to determining how much material of various sizes should be wandering through the local interstellar medium. Almost universally, these models predict that smaller objects should vastly outnumber larger ones. The interstellar medium, in theory, ought to be thick with fragments the size of football fields and city blocks, while giants like Atlas should be rare exceptions. And yet, the puzzle remains. In practice, our first sample of interstellar objects has delivered one lightweight enigma, one textbook comet, and one possible titan. The statistics don't yet add up, and Rubin's all-seeing eye may be the only way to reveal whether Atlas is an outlier or a herald of something we never expected. The exact scale depends on the assumed ejection mechanisms and the survival rates of debris, but most frameworks point towards steep size distributions where kilometer-scale bodies are rare compared to 100-meter fragments. Here, the lifetime of protoplanetary disks adds urgency to the theoretical problem. Around young stars, disks typically dissipate within 5 to 10 million years, eroded by stellar radiation through photoevaporation and drained by accretion onto the central star. This narrow window places tight limits on how much material can be ejected during the disk phase, as opposed to later epochs when planetary scattering becomes dominant. Atlas, whether typical or anomalous, is part of that archive. Its mystery is not just about statistics. It is about what these silent messengers can reveal about the deep processes that shape galaxies themselves. Population synthesis efforts attempt to weave these diverse physical processes into coherent predictions about the characteristics of interstellar visitors. By modeling stellar formation rates, cluster dynamics, planetary system architectures, and ejection efficiencies, theorists can estimate how many objects of different sizes should pass through the solar system per unit of time. Yet the models vary widely. Current frameworks span orders of magnitude in their predictions, reflecting the uncertainties built into their physical assumptions. Some suggest encounter rates of roughly one object per year larger than 100 meters, while others predict rates an order of magnitude higher or lower. Against this backdrop of uncertainty, 3I Atlas and its predecessors stand as the first empirical constraints, data points that begin to tether theory to reality. Each detection narrows the possibilities, forcing models to adjust, revise, or collapse under the weight of new evidence. In the end, the reservoir problem is more than a question of statistics. It is the bridge between local observations, fleeting pinpricks of light in our telescopes, and galactic-scale processes operating across billions of years. To solve it is to connect the passage of a single comet-like stranger with the deep history of the Milky Way itself. Each interstellar visitor is a sample of a vast unseen population, carrying within it clues about conditions of formation, mechanisms of ejection, and survival processes operating in stellar environments we may never be able to visit directly. As detection rates rise and sample sizes grow, population statistics will evolve from speculation into precision measurement. The apparent anomalies surrounding 3I Atlas may one day dissolve into the noise of early, sparse data, or they may instead signal genuine surprises about how matter moves through the spaces between stars. But before those questions can be settled, astronomers must confront an even stranger curveball: the chemical puzzle Atlas delivered. Among the gases and dust of its coma, spectroscopic analysis uncovered something no one expected: nickel emissions with no corresponding iron signals. Part 7. The nickel without iron mystery. High-resolution spectroscopy from the Very Large Telescope revealed this anomaly in Atlas's coma, a result that left researchers genuinely unsettled. In cosmic chemistry, nickel and iron are siblings, forged in similar nucleosynthetic processes and usually found together in comparable proportions. To see one without the other suggests that Atlas is hiding a story stranger than its mass or its orbit alone could tell. Multiple nickel emission lines shone prominently in the infrared, while iron remained conspicuously absent from the same spectra. This chemical asymmetry challenges the most basic assumptions about metallic emissions in cometary environments, and adds yet another entry to Atlas's growing list of anomalies. The observation itself was simple, but the implications were striking. Using high-resolution spectrographs, the Very Large Telescope detected several distinct atomic nickel transitions in the 700-900 nanometer range during observations in August 2025. These lines stood out clearly above the noise, with signal intensity strong enough to allow quantitative analysis of both nickel production rates and its spatial distribution within the coma. But the iron lines those astronomers fully expected to find at nearby wavelengths were simply not there. Instead, the spectra showed nothing more than background noise, consistent with upper limits on iron emission that fell well below typical detection thresholds for comets at similar heliocentric distances. The absence of iron where it should have been, side by side with glowing nickel, struck the observing teams as deeply unnatural, as if Atlas carried within it a chemistry rewritten by conditions alien to our solar system. This absence is not merely a failure of detection or a case of signals lost in the noise. It represents a genuine chemical peculiarity, one that demands an explanation. The context makes the anomaly even more significant. In both meteorites and cometary material, nickel and iron typically exist in similar chemical forms, often locked together in alloys or parallel compounds. Seeing nickel in abundance without its iron counterpart is like discovering a forest filled entirely with oaks but no maples, in a region where both species are known to coexist. Derived production rates from the VLT spectroscopy revealed a sharp dependence on heliocentric distance. As 3I Atlas approached the Sunday, emissions of both nickel and cyanogen rose dramatically as the solar distance decreased, following power law relations with exponents around 8 to 9. Such a steep brightening points to a strong temperature dependence in whatever process is releasing these species into the gas phase. In other words, the closer Atlas drifted toward the Sun, the more insistently it whispered its chemical oddities into our telescopes, nickel glowing where iron should have been, cyanogen swelling with heat, as though some hidden reservoir of alien chemistry were being slowly unlocked. Such a steep escalation suggests that the emission mechanism operates near a critical temperature threshold. As solar heating warms the surface of the nucleus, some process suddenly becomes efficient at liberating nickel atoms into the coma, where they radiate the spectral lines now observed. The mathematics of this temperature dependence provides important clues about the underlying physical and chemical processes at work. Traditional cometary chemistry offers several possible explanations for metal emissions, but none align neatly with Atlas's unusual profile, where nickel shines while iron remains invisible. Direct sublimation of metal-rich minerals, for example, generally requires temperatures far higher than those reached at Atlas's observed heliocentric distance during the VLT campaign. That pathway cannot fully account for the anomaly. Something subtler must be at play. One plausible mechanism is photon-stimulated desorption, a process in which incoming solar photons knock individual atoms loose from the surface or from mineral grains, releasing them into the coma without requiring the extreme bulk heating needed for wholesale sublimation. This would explain both the sudden onset of nickel emission near a thermal threshold and the absence of corresponding iron. If the two elements are bound in different mineral phases or surface layers that respond unequally to solar radiation, solar ultraviolet radiation can break chemical bonds in surface materials, liberating atoms that would otherwise remain bound under purely thermal conditions. If 3I Atlas contains nickel-bearing compounds that are particularly susceptible to photodissociation, while iron-bearing phases remain more tightly bound, this could explain the chemical selectivity now observed. Alternative hypotheses point toward the thermal breakdown of organometallic compounds or metal-carbonyl complexes that might exist within the nucleus. Such materials could decompose at relatively low temperatures, releasing metal atoms through chemical reactions rather than through direct sublimation of refractory minerals. If nickel forms more volatile compounds than iron under Atlas's alien conditions, then differential release could naturally produce the abundance pattern astronomers are now witnessing. Nickel lines flaring bright in the infrared, while iron stays locked away in the dark. In that scenario, the mystery shifts from being one of missing elements to one of exotic chemistry, a cometary nucleus preserving compounds rarely, if ever, seen in the solar system, now unraveling under the touch of starlight. Cross-referencing with JWST observations only deepens the chemical puzzle. The telescope detected a carbon dioxide-rich coma with unusually high CO2 to water ratios, painting a picture of formation under extremely cold conditions, far beyond the carbon dioxide snowline. When combined with the prominent nickel emissions, this chemistry suggests a birthplace fundamentally different from the typical comet-forming regions of our own solar system. These chemical fingerprints point to formation in the outermost reaches of stellar systems, where temperatures remain low enough for exotic ices and metal-rich compounds to condense. The long interstellar journey would have preserved these primordial compositions, allowing 3I Atlas to carry with it a chemical time capsule from alien stellar nurseries billions of years ago. It is as though the comet itself is a messenger bearing not just dust and ice, but archaeological evidence of other suns, frozen into its body and released only now as it awakens under the light of ours. What this chemistry does not prove deserves special attention, particularly given the waves of media speculation. Some commentators noted that the nickel without iron pattern vaguely resembles certain industrial alloys, and from there leapt to technological interpretations. But this is a leap not supported by the evidence. The metallic emissions observed in Atlas's coma arise from well-understood atomic physics, not from processes of engineering. There is no spectroscopic evidence pointing to manufacturing, only to unusual but natural chemistry. Here, the issue of scientific literacy in the media becomes crucial. Second-tier websites and social media accounts amplified the nickel anomaly into narratives of artificial origin stories with no basis in peer-reviewed analysis. The Very Large Telescope team, by contrast, presented their spectroscopic results as examples of interesting but natural chemistry, not as evidence of manufactured objects masquerading as comets. Distinguishing genuine scientific anomalies from sensationalist misinterpretations is essential for the public's understanding of how astronomy works. Unusual chemistry deserves careful investigation and explanation, but unusual does not automatically imply artificial. The universe contains no shortage of natural processes capable of producing unexpected elemental abundance patterns. There are historical parallels within solar system comet research. Several comets have displayed metallic emission ratios that initially puzzled investigators, only to later find natural explanations involving grain composition, temperature effects, or photochemical processing. This is how the scientific method works. Hypotheses are proposed, predictions tested, explanations refined as new data become available. The nickel emission lines themselves are not just anomalies. They provide quantitative constraints on gas production rates and kinetic temperatures within the coma. The widths of the spectral lines reveal broadening from thermal velocities and bulk motion, while the intensity ratios constrain excitation conditions and density distributions. Together, these measurements transform a mystery into a laboratory. The coma of Atlas becomes a place where atomic physics and interstellar history intersect, whispering clues about the processes unfolding in real time. This information feeds directly into physical models of coma structure and evolution. Visual representations of the spectroscopic data help clarify what the VLT actually observed. Imagine a spectrum, with wavelength plotted on the horizontal axis and brightness on the vertical. The nickel lines appear as sharp peaks, each rising at precise wavelengths where atomic transitions release their characteristic photons. The iron lines, by contrast, should occupy their own predictable positions across the spectrum. Yet in those regions, the graph shows nothing but flat noise silence where a signal should have been. The spatial distribution of nickel emission within the coma adds another layer of mystery. If nickel originates from discrete active regions on the nucleus, then high-resolution spectroscopy should reveal localized structures, peaks tied to jets or vents. If instead it arises from distributed grain processing, the pattern would appear more diffuse and uniform, smeared across the coma. Current observations lack the spatial resolution to map this structure in detail. But with future high-resolution instruments, whether ground-based adaptive optics or space-based telescopes, we may finally be able to trace the nickel emission back to its true source. Until then, the picture remains blurred, like a riddle glimpsed through fog. Spectroscopy could ultimately distinguish between localized and distributed emission scenarios. The next generation of extremely large telescopes, coming online in the years ahead, will offer unprecedented spatial and spectral resolution to probe cometary chemistry in ways never before possible. The temporal evolution of nickel emissions, as 3I Atlas approaches perihelion, will provide crucial tests of the proposed release mechanisms. If photodesorption dominates, emission rates should correlate directly with the intensity of solar flux. If thermally controlled processes are responsible, the emissions should instead follow the nucleus's surface temperature profile, complete with time lags corresponding to thermal diffusion through subsurface layers. But these observations represent more than a mere chemical curiosity. Metallic emissions in cometary comae are direct probes of refractory element abundances and chemical processing in environments that preserve the primordial compositions of stellar system formation. Understanding these processes sheds light not only on the conditions of our own solar system's infancy, but also on the hidden chemical histories of distant planetary nurseries. The nickel without iron mystery exemplifies how 3I Atlas continues to defy expectations across multiple domains of observation: mass, dynamics, morphology, chemistry. It is as though every new dataset turns the object into another paradox, each clue unraveling certainty rather than delivering it. From its anomalous mass to its peculiar morphology to its unusual chemistry, this interstellar visitor seems determined to challenge astronomy's assumptions at every level of analysis. Persistent anomalies have historically driven scientific progress, forcing researchers to question fundamental assumptions and build better theoretical frameworks. Whether 3I Atlas ultimately yields to conventional explanations or demands genuinely new physics, its strange properties are already expanding our understanding of interstellar chemistry and cometary evolution. Mysteries like this are what kept the debate over Oumuamua alive for years, generating dozens of theoretical papers and repeated observational campaigns. The scientific process thrives on such puzzles, using them as fuel for better instruments, more detailed observations, and more sophisticated models. But what happens when someone argues that the accumulated anomalies point not toward natural processes, but toward a technological explanation? Part 8. The Technological Hypothesis. The technological interpretation of 3I Atlas arises from a convergence of unusual features that, when considered together, strain conventional explanations. Advocates point to the statistical improbabilities in its orbital geometry, the lower limit mass problem, its precise crossings of the planetary plane, and its unusual chemical signatures as circumstantial evidence of artificial rather than natural origins. The ecliptic alignment is often cited as the foundation of these arguments. Atlas approaches the solar system with an orbital inclination of only 4.1 degrees relative to the planetary plane, a configuration that would occur randomly in only about one case out of 500 for interstellar objects arriving from arbitrary directions. While not impossible, such alignment has raised eyebrows among researchers who track visitor statistics. Among the most prominent voices urging the scientific community to take such possibilities seriously has been Harvard astronomer Avi Loeb. Known for his earlier advocacy of technological hypotheses regarding Oumuamua, Loeb has again highlighted Atlas's improbable alignment and other anomalies as reasons not to dismiss the artificial interpretation outright. Though his presentations emphasize scientific methodology rather than definitive conclusions, Avi Loeb's approach often involves calculating the probabilities of various natural scenarios and weighing them against alternative explanations, invoking artificial origins only when conventional physics appears insufficient. The intersection with Jupiter adds a layer of practical urgency to what might otherwise remain a theoretical debate. Several papers by Loeb, Hibbard, and collaborators have outlined technically challenging but potentially feasible mission concepts to redirect NASA's Juno spacecraft toward a close encounter with 3I Atlas during its March 16, 2026 passage near Jupiter. Such missions would require highly complex orbital mechanics, involving carefully timed maneuvers that exploit Jupiter's immense gravity to alter Juno's trajectory into an intercept course. The fuel requirements push against the limits of engineering, and success would hinge on precision execution and split-second timing. Yet the proposals demonstrate genuine scientific ambition, a determination to gather close-range data rather than relying solely on the distant eyes of Earth-based and space-based telescopes. For some, Atlas represents a test case, an opportunity to decide whether its mysteries can be unraveled by physics alone, or whether the possibility of something more should remain on the table. Mass estimates add further fuel to the technological speculation by straining conventional explanations. If 3I Atlas truly weighs tens of billions of tons, while exhibiting minimal non-gravitational acceleration despite clear signs of active outgassing, then traditional cometary physics struggles to reconcile such behavior. Proponents of the technological hypothesis suggest that controlled propulsion could explain the disconnect between visible cometary activity and the absence of orbital perturbations. In their view, Atlas's apparent silence in the face of outgassing is not a failure of physics, but the hint of an engineered system regulating its own trajectory. Yet natural alternatives remain both plausible and compelling. Forward scattering of dust could create the observed sunward glow without invoking exotic mechanisms. A carbon dioxide-rich ice chemistry could produce activity patterns that diverge significantly from water-dominated comets. Even unusual grain-size distributions or compositions could alter the efficiency with which escaping gas transfers momentum to the solid nucleus, mitigating the expected rocket effect without requiring any artificial control. The debate is not settled, but the mere fact that Atlas's properties can be read through such different lenses, natural or artificial, underscores just how far this interstellar visitor has pushed the boundaries of interpretation. The debate inevitably turns toward the burden of proof when evaluating extraordinary claims. The absence of iron emissions or the presence of anomalously weak accelerations may strike some as suggestive, perhaps even unsettling, but they do not constitute positive evidence for artificial propulsion. In science, the standard remains firm. Extraordinary claims require extraordinary evidence. That evidence would need to be unmistakable, resolved imagery revealing manufactured structures, radar signatures inconsistent with natural materials, or trajectory changes beyond what sublimation physics could ever predict. Anything less remains in the realm of speculation. Here lies the challenge of communication, translating scientific uncertainty into public discourse without distortion. Headlines portraying Atlas's perihelion passage on the far side of the Sun as a form of intentional evasion are not revelations of agency, they are misinterpretations of basic orbital mechanics. 3I Atlas follows a hyperbolic path, defined by its incoming velocity vector and the gravitational field of the solar system, not by any conscious navigation. Both NASA and ESA have adopted a conservative stance. Treat Atlas as a natural object, unless and until compelling data prove otherwise. This reflects the discipline of scientific conservatism, favoring conventional explanations until the weight of evidence demands rejection. For now, agencies continue to track the object with every available asset, gathering data with patience, resisting premature conclusions about its origins. Testable predictions remain the dividing line between scientific speculation and unfounded conjecture. If 3I Atlas were in fact artificial, it might exhibit sudden post-perihelion trajectory shifts that cannot be explained by cometary outgassing alone. Such deviations would appear as anomalous accelerations in the continuous astrometric monitoring carried out by ground-based and space-based telescopes. Other potential signatures could include unexplained thermal emission patterns visible to infrared observatories, coherent radio transmissions inconsistent with natural sources, or polarization effects that defy the scattering properties of ordinary cometary dust. Detecting such phenomena is extraordinarily difficult with current technology, but they represent the kind of concrete tests that could separate natural explanations from artificial ones. The challenge lies in the geometry of observation. Atlas reaches perihelion on the far side of the Sun relative to Earth, forcing a months-long observational blackout as it disappears into the solar glare. This loss of coverage is dictated by orbital mechanics, not by deliberate concealment. Yet the effect is the same. The object will remain unseen during its most dynamic phase of activity. When it re-emerges from behind the Sun, the first fresh datasets will carry enormous weight. Every arc second of its trajectory, Every spectral anomaly, every flicker of light, will be scrutinized not only as evidence for or against the artificial hypothesis, but as a test of our ability to understand matter moving between the stars. The Parker Solar Probe's Whisper camera offers a rare vantage point during perihelion, observing 3I Atlas from solar perspectives inaccessible to Earth-based telescopes. Such observations could reveal activity patterns or morphological changes that remain invisible from terrestrial viewpoints, providing critical data during the blackout period. Within this context, the technological hypothesis serves an important role in scientific discourse, even if it is ultimately disproven. It provides alternative frameworks for interpreting unusual data, forces more rigorous testing of conventional explanations, and motivates better observations designed to discriminate between competing models. Science thrives on intellectual diversity and the skeptical re-examination of assumptions. Yet maintaining proper skepticism requires a careful distinction between legitimate scientific speculation and unfounded conspiracy narratives. The technological interpretation of 3I Atlas represents a testable scientific hypothesis, not an ungrounded claim. Its proponents publish calculations, orbital analyses, and observational predictions that can be evaluated against data by standard scientific methods. Whether the outcome confirms a natural giant or suggests something stranger, the act of framing falsifiable predictions ensures that the debate advances scientific knowledge rather than dissolving into unanchored speculation. The cultural context surrounding these debates reflects a broader societal fascination with the possibility of extraterrestrial intelligence. After decades of SETI searches, and more recently, official government acknowledgments of unidentified aerial phenomena, public interest in potential technological artifacts has grown considerably. This enthusiasm can act as a double-edged sword, motivating scientific inquiry on one hand, while distorting the interpretation of ambiguous data on the other. Responsible scientific communication requires presenting multiple hypotheses while maintaining appropriate levels of confidence in each explanation. The technological interpretation of 3I Atlas deserves mention as one possibility among many, but the evidence currently available remains insufficient to elevate it above more conventional alternatives that involve unusual yet entirely natural cometary physics. The media amplification cycle illustrates how speculative science can morph into definitive claims through repetition. Early articles that carefully introduced technological possibilities as hypotheses requiring further investigation can, after successive rounds of reporting and social media sharing, transform into sweeping assertions about probable artificial origins. Crucial caveats and uncertainties are often stripped away in the process, leaving the public with a distorted impression of scientific consensus. In this sense, Atlas is not only a test of astrophysics, but also of how science, culture, and imagination interact when faced with phenomena that blur the line between the familiar and the unknown. Educational opportunities emerge naturally from these debates about hypothesis testing, statistical reasoning, and the scientific method itself. 3I Atlas provides a rare, real-time case study in how scientists approach unusual observations, generating multiple explanations, designing tests to distinguish between alternatives, and refining understanding as new data accumulate. The process of peer review plays a critical role in evaluating unconventional claims. While preliminary analyses and conference presentations may explore speculative ideas, definitive conclusions require rigorous evaluation by expert reviewers who scrutinize methodology, statistical treatment, and interpretation of results. This quality control mechanism ensures that legitimate scientific inquiry remains clearly separated from unfounded speculation. Future observations will deliver decisive tests of the technological hypothesis. Continuous astrometric tracking, detailed spectroscopic analyses, and even the possibility of spacecraft encounters represent the pathways to resolution. If 3I Atlas exhibits behavior consistent with the known physics of comets, then technological interpretations will naturally fade into the background, serving only as a reminder of how science thrives by confronting uncertainty with falsifiable ideas. If future observations reveal genuinely anomalous features, the technological hypothesis will gain credibility and drive more detailed investigations. The critical window for such decisive tests spans the next 18 months, as 3I Atlas completes its passage through the inner solar system and eventually emerges from behind the Sun, where Earth-based instruments can resume continuous tracking. This extended campaign provides multiple opportunities to test predictions under both natural and artificial origin scenarios. Regardless of the final outcome, the very discussion of technological hypotheses underscores the importance of open-mindedness balanced by rigor. Science advances by considering unconventional possibilities, while demanding extraordinary evidence for extraordinary claims. This balanced skepticism paired with imagination is what transforms puzzles into progress. Yet there is another speculative framework equally fascinating, and perhaps more firmly rooted in astrophysical theory. The possibility that objects like 3I Atlas act not as artifacts of technology, but as seeds of planetary formation, fragments wandering between stars that carry with them the raw materials for building new worlds. Part 9. The Planet Seeding Hypothesis. Suzanne Falsner's planet seeding hypothesis stands among the most intriguing theoretical frameworks for interpreting the mass of interstellar visitors like 3I Atlas. The concept suggests that interstellar objects, once captured by young stellar systems, could bypass traditional planetary formation bottlenecks and jumpstart the growth of giant planets during the fleeting window, when protoplanetary disks still retain sufficient mass to sustain runaway accretion. The traditional paradigm of planet formation faces a serious timing problem. Gas giants must accumulate enough bulk before their natal protoplanetary disks are lost to photoevaporation or consumed by stellar accretion. This window typically lasts only 5 to 10 million years after a star's birth, a strict deadline that leaves little room for slow, incremental growth. Core accretion models in particular struggle against what astronomers call the meter-size barrier. As solid particles in a protoplanetary disk collide and stick together, growth becomes increasingly inefficient at the meter scale. Aerodynamic drag with the surrounding gas tends to spiral meter-sized bodies into the star before they can grow larger, effectively stalling planet formation. The puzzle of how planetary embryos leap beyond this barrier to become kilometer-scale planetesimals remains one of the most enduring mysteries in astrophysics. Interstellar objects like Atlas, if captured at the right time, could act as ready-made seeds, fully formed planetesimals injected into a young disk, instantly providing the mass and scale needed to leapfrog the meter barrier and trigger rapid accretion. In this vision, visitors like 3I Atlas are not merely anomalies to be explained, but cosmic catalysts that may have helped shape the very architecture of planetary systems across the galaxy. The tendency of planetesimal-sized bodies to spiral into their parent stars under aerodynamic drag before they can accumulate into larger gravitationally bound objects remains a central obstacle in planetary science. Small debris experiences significant gas drag within a protoplanetary disk, leading to orbital decay that prevents growth into true planetary scales. The capture of interstellar objects offers an elegant solution to this timing dilemma. If young stellar systems can gravitationally capture pre-existing kilometer-scale objects drifting through the interstellar medium, these ready-made seeds could bypass the slow, vulnerable growth phase and immediately begin accreting gas and dust from their host disks. Captured bodies would already carry enough mass to resist aerodynamic drag, serving as gravitational scaffolds upon which new worlds could assemble. Instead of struggling against the meter-sized barrier, the system inherits a fully formed nucleus, capable of snowballing into a planetary giant within the narrow time window before the disk evaporates. In this framework, interstellar visitors like 3I Atlas are not accidents of celestial wandering, but potential agents of planetary genesis, silent carriers of material, seeding the architecture of solar systems wherever they are ensnared. Conference presentations at the 2025 European Planetary Science Congress and the Division for Planetary Sciences meeting unveiled updated simulations supporting this capture seeding scenario. A new model indicates that massive stars capture interstellar objects more efficiently than lower mass systems, creating a potential correlation between stellar mass and the occurrence of giant planets, a trend that intriguingly mirrors observed exoplanet demographics. The mechanism operates through gravitational focusing effects during close encounters between interstellar visitors and young stellar systems. More massive stars generate deeper gravitational wells, enlarging the effective cross-section for capture. Moreover, massive stars often form within dense stellar clusters, where the encounter rate with interstellar debris remains high during the critical early phases of disk evolution. This combination dramatically increases the odds that large, wandering planetesimals are ensnared. Recent press coverage has begun to explore the idea that objects like 3I Atlas could theoretically bypass the traditional barriers to planet formation and accelerate growth processes. Importantly, these explanations emphasize that seeding by capture is not a replacement for conventional core accretion, but rather a complementary pathway, a mechanism potentially operating in parallel with traditional processes under certain stellar environments. In this light, Atlas becomes more than a puzzle. It becomes a lens through which to consider the very origins of planets themselves. The chemical connection adds a layer of plausibility to seeding scenarios involving 3I Atlas. Specifically, JWST detected a carbon dioxide-rich outflow, with abundance ratios suggesting formation far from its parent star beyond the CO2 snowline, where temperatures remain below 125 degrees Celsius. Such frigid conditions are typical of objects originating in the outermost reaches of stellar systems. An interstellar visitor captured under these circumstances would carry with it exotic volatile compositions, introducing chemical diversity into its new host disk. This infusion of alien ices and refractories could help explain some of the compositional variety observed in exoplanetary atmospheres. Different stellar systems are likely to produce debris with different ice chemistries and refractory abundances, so the capture process would effectively blend materials from multiple stellar environments, a form of galactic cross-pollination. Here, population statistics become crucial to evaluating the viability of the seeding hypothesis. If the Rubin Observatory's legacy survey of space and time uncovers large numbers of interstellar visitors in the coming decade, then capture rates in young stellar systems shift from speculative to statistically plausible. In this framework, Atlas is not just a curiosity, it is a messenger of chemical diversity, a fragment that hints at how planetary systems might inherit matter from far beyond their own stars. If 3I Atlas proves to be exceptionally rare, then seeding scenarios lose credibility simply through the lack of sufficient raw material. Yet current theoretical work suggests that young stellar systems may capture interstellar objects at rates high enough to influence planetary outcomes. In dense star-forming regions, the environment offers both frequent encounters with drifting debris and gravitational conditions favorable for permanent capture. The process becomes most efficient during the first few million years, when stars still retain massive circumstellar disks, reservoirs of gas and dust, capable of rapidly accreting onto captured seeds. The idea of planetary seeding is not entirely new. Its historical precedents stretch back decades, but recent advances in theoretical modeling have added sharpness to the concept, providing quantitative predictions of capture rates, size distributions, and subsequent evolutionary paths. These models bridge astrophysical dynamics with observable demographics. Making the hypothesis more than speculation, it becomes a testable framework. In this context, Atlas is not just a wandering anomaly. It may be a glimpse into the mechanisms that shaped planetary systems across the galaxy, a fragment that helps explain why giants form in some environments and not in others. Earlier studies suggested that 10 million or more Oumuamua-scale seeds could exist per protoplanetary disk during peak formation epochs, representing a radical rethinking of traditional planet formation paradigms. In this vision, young disks are not closed systems, but open laboratories, constantly seeded by the passage of interstellar debris. The efficiency of capture depends on several key factors: the relative velocity between interstellar visitors and their target stellar systems, the mass and structure of the host disk, and the dynamical environment, whether the star forms in isolation, within a binary, or inside a dense stellar cluster where gravitational focusing enhances encounter rates. Different stellar birth environments would naturally produce different capture signatures and seeding efficiencies, shaping planetary demographics on a galactic scale. But there are counter-arguments. Critics emphasize the remaining uncertainties in capture mechanics, the survivability of captured objects, and the migration processes that determine where such seeds ultimately end up within their host disks. Capturing an object is only the first step. For seeding to matter, the body must survive long enough and in the right location to accrete material and grow into something larger. Thus, Atlas raises a deeper question: is it merely a wanderer, or an example of the hidden architects that may have shaped the diversity of planetary systems we see today? The seed must first survive tidal perturbations, avoid ejection through subsequent gravitational encounters, and then migrate into regions of the disk capable of sustaining rapid accretion. The evolution of the disk structure itself adds layers of complexity to seeding scenarios. Young protoplanetary disks undergo rapid shifts in density and temperature profiles, along with turbulent mixing that could either enhance or inhibit the survival and growth of a captured seed. Understanding these processes requires sophisticated magnetohydrodynamic simulations that couple disk evolution with planetary formation physics. Only by modeling the interplay between turbulence, migration, and gas drag can researchers evaluate whether interstellar seeds truly have a chance to become planetary cores. For now, the observational signatures of seeding remain largely theoretical. Successful planet formation around captured interstellar seeds could produce chemical or isotopic anomalies detectable in the atmospheres of mature exoplanets, fingerprints of alien origins carried across light years. Yet, such signatures would be extraordinarily subtle, far beyond the reach of current observational capabilities. Atlas, then, serves as a reminder: even if seeds exist, their stories may remain hidden, woven into the chemistry of planets we cannot yet study in sufficient detail. The demographics of exoplanets may provide indirect evidence to test the predictions of the seeding hypothesis. If capture processes play a significant role in shaping planetary outcomes, they should leave statistical fingerprints in the distributions of planetary mass, orbital characteristics, and host star correlations revealed by large-scale exoplanet surveys. Some of these patterns may already be present, hidden within existing datasets. The theoretical framework, however, requires careful distinction between what current models can reliably predict and what remains speculative extrapolation, awaiting future observational tests. Capture cross-sections and gravitational focusing effects rest on well-understood physics, but the subsequent evolutionary stages, how seeds interact with turbulent disks, how they alter local chemistry, how they migrate, depend on complex processes of disk chemistry and dynamics that remain poorly constrained by present-day observations. In this sense, exoplanet demographics become both a laboratory and a mirror, a way to glimpse the unseen histories of interstellar seeds while reminding us of the limits of our own models. Atlas, with its anomalous chemistry and massive scale, sharpens this question: was it itself once a mist seed, or merely a messenger pointing us toward the hidden architecture of planetary origins? Visual representations of the seeding process help clarify the proposed mechanism. Imagine an animation showing an interstellar object plunging into a young protoplanetary disk, where gas drag gradually circularizes its orbit. Once settled, the captured body begins to sweep up gas and dust, growing larger with every pass through the disk. The physics resembles conventional core accretion, but with one critical difference: the head start provided by a pre-existing solid nucleus. Where traditional core accretion requires the painstaking assembly of kilometer-scale planetesimals from dust grains, a process that can take millions of years, captured seeds arrive already ready-made, carrying the mass needed to bypass early bottlenecks. The timescale advantage becomes stark when comparing seeded scenarios with conventional planet formation. In the traditional pathway, disks must laboriously grow small planetesimals over millions of years before planetary embryos can accumulate enough mass to trigger runaway accretion. Captured seeds begin that process already at the kilometer scale, potentially reducing total formation timescales by significant margins. In this light, interstellar objects like 3I Atlas are more than wanderers. They are potential shortcuts in the cosmic assembly line, collapsing the slow climb toward planetary mass into a leap sparked by alien fragments adrift between stars. Future theoretical work will aim to refine capture rate predictions and evaluate survival probabilities under realistic scenarios of disk evolution. These calculations require the integration of stellar cluster dynamics, interstellar object population models, and the detailed physics of protoplanetary disks, a multi-scale challenge that pushes the limits of current computational capabilities. The connection between 3I Atlas and planetary seeding remains speculative, constrained by present observational limitations. Yet the object's anomalous properties make it an intriguing test case for evaluating whether massive interstellar visitors could plausibly act as catalysts of planet formation. If future research demonstrates that such objects are common, the seeding hypothesis will gain credibility as a viable complement to standard theories. But if they prove to be rare, then conventional mechanisms of planet formation will continue to dominate our theoretical frameworks. Atlas thus stands at a crossroads, either an exception that highlights the strength of traditional models, or the first whisper of a larger truth that worlds themselves may sometimes begin with the capture of a wandering fragment from another star. The broader implications extend far beyond any single object, reaching into profound questions about how matter is exchanged between stellar systems and how such exchanges influence galactic-scale evolution. If seeding processes operate efficiently, they represent a previously unrecognized pathway for chemical and physical communication across interstellar distances. In this vision, comets and planetesimals become not just debris, but cosmic couriers, transporting ices, metals, and organics between stars scattered light-years apart. Such a perspective forces us to reconsider the very singularity of planetary systems. Are worlds truly isolated creations, sculpted solely within the confines of their parent star's disk? Or are they part of a shared evolutionary web where fragments from countless suns contribute to each other's formation stories? Answering these questions requires bridges linking observational astronomy, theoretical astrophysics, and planetary science in ways that transcend traditional disciplinary boundaries. Each field holds only part of the puzzle. Only together can they illuminate the full cosmic tapestry. And yet, beyond frameworks and models, one question lingers like a shadow. Why now? Why is humanity suddenly encountering such massive, enigmatic interstellar visitors at this exact moment in its history? The convergence of technological capacity, observational geometry, and sheer cosmic coincidence that enabled the discovery and detailed characterization of 3I divided by Atlas stands as a remarkable intersection of multiple converging factors. Understanding why we are detecting such a massive interstellar visitor now requires examining three intertwined threads: the observational revolution transforming astronomy, the specific geometrical advantages that rendered this object detectable, and the broader question of whether we are witnessing nothing more than statistical fluctuations or signs of a genuine physical phenomenon at work. The observational infrastructure that made the discovery possible has reached a level of sophistication unparalleled in human history. The Southern Atlas Survey came online in 2022, extending continuous sky coverage across the southern hemisphere and complementing the original Hawaiian installations. This global network now enables uninterrupted monitoring of transient phenomena, as the rotation of Earth brings different observatories into optimal viewing conditions. In effect, humanity has built a planet-sized eye, one that can now notice fleeting messengers from beyond the stars. Messengers that, only a decade ago, would have slipped silently past, unrecorded, and unseen. Rapid response channels now link Discovery telescopes with follow-up assets, compressing reaction times from weeks to mere hours. When Atlas Chile first detected 3I divided by Atlas on the 1st of July 2025, the Minor Planet Center classified it as a potentially significant object within days. The Hubble Space Telescope followed up less than 3 weeks later, and JWST spectroscopy was underway just over a month after discovery. Such coordination marks a quantum leap in astronomical responsiveness, a stark contrast to the slow, fragmented cadence of past decades. Yet technology is only half the story. Geometry tilted the scales in Atlas's favor. The object approached along a trajectory almost perfectly aligned with the ecliptic plane, the cosmic stage, where most solar system surveys focus their attention. This meant that a vast infrastructure, optimized for tracking asteroids and comets, was already pointing in the right place at the right time. The alignment kept 3I divided by Atlas within the operational parameters of multiple ground and space-based facilities, allowing sustained follow-up without the usual interruptions caused by high inclination or retrograde interstellar paths. It raises an unsettling thought. Perhaps Atlas was not just discovered because it was there, but because its geometry bent the odds, slipping into our search field like an intruder who knows exactly where the security cameras are pointed. Objects arriving on highly inclined or retrograde trajectories would be systematically harder to discover, let alone characterize, potentially biasing our first sample toward ecliptic-aligned interstellar visitors like 3I divided by Atlas. This geometric favoritism could mean that our current sense of what is typical is already skewed, built on a foundation of convenience rather than cosmic truth. Meanwhile, the media amplification cycle demonstrates how anomalous framing can magnify attention. Early reports emphasized Atlas's extraordinary inferred mass, drawing headlines and speculation, while glossing over the fact that those estimates rested on assumptions about outgassing physics, assumptions that are now under careful scrutiny. Initial calculations, based on the absence of measurable non-gravitational acceleration, produced values that startled even seasoned astronomers. But such numbers are not immutable facts. They are working hypotheses, vulnerable to revision as data are reanalyzed and models refined. This is where viewer discretion becomes essential. Scientific discovery is not a finished story delivered to the front page, it is a process. The anomalous mass estimates, the strange chemical signatures, the demographic puzzles that surround 3I divided by Atlas are active frontiers of inquiry, not settled conclusions. To treat them as certainties is to mistake the fog of exploration for the clarity of arrival. Responsible science communication must carefully separate preliminary findings from established results, while still preserving the sense of wonder that naturally accompanies a truly remarkable discovery. Interstellar objects, like 3I divided by Atlas, test this balance. Their very strangeness ignites public fascination, yet scientists know that early estimates, whether of mass, chemistry, or dynamics, are fragile, subject to revision as new data emerge. Into this landscape of uncertainty enters an unusual opportunity, the chance to view Atlas not only from Earth, but from the vantage point of space-borne observatories. The Parker Solar Probe's Whisper camera is expected to record Atlas during its late September to early November 2025 perihelion passage, providing rare coverage from the sun-facing side, just as the object slips beyond the reach of ground-based telescopes, hidden in the glare. Such perspectives are more than complementary. They are transformative. A spacecraft riding close to the sun will see scattering angles, dust geometries, and outgassing patterns invisible from Earth's line of sight. It may reveal whether the enigmatic sunward glow is merely a trick of perspective, or the imprint of physics not yet fully understood. The evolving structure of Atlas's tail, the balance of gas and dust, the very morphology of the coma, each could shift dramatically when viewed from a different celestial angle. To understand Atlas near perihelion, we must abandon the illusion of a single vantage point. Only by stitching together multiple lines of sight, Earth, space telescopes, solar probes, can we hope to disentangle geometry from substance, illusion from reality. Sample size effects provide the simplest explanation for the apparent statistical anomalies in the demographics of interstellar visitors. With only 3 confirmed examples, Oumuamua in 2017, 2I divided by Borisov in 2019, and 3I divided by Atlas in 2025, attempting to draw robust conclusions about entire populations of galactic debris is, at best, premature and, at worst, misleading. With so little data, any early fluctuation can masquerade as a trend. The history of astronomy is littered with warnings. Small samples generate illusory patterns that later dissolve into noise once catalogs grow large enough. The alternative interpretation, more unsettling, is that 3I divided by Atlas genuinely occupies the rare tail of the interstellar size distribution, a statistical unicorn that, by sheer coincidence, emerged during humanity's very first systematic surveys. Its arrival at this early stage is improbable, but not impossible. Outliers occur precisely because distributions have tails, and when they appear, they etch themselves into memory, reshaping expectations for decades. What sharpens this paradox is the ongoing technological revolution. Hardware improvements across multiple domains of observation have multiplied our sensitivity to faint, distant objects, while simultaneously sharpening our astrometric precision to track minute trajectories with accuracy once thought impossible. Ground-based adaptive optics systems peel back the blur of Earth's atmosphere, rendering stars and comets with near-space clarity. Space telescopes, liberated from atmospheric absorption, extend our vision into spectral regions inaccessible from the ground. And the latest generations of detectors achieve higher quantum efficiency and lower noise, capturing signals that would have slipped into darkness just a decade ago. It is at this intersection between statistical chance and unprecedented instrumental sensitivity that the true enigma lies. Did we find 3I divided by Atlas because it is representative of what truly populates interstellar space? Or because luck delivered us an improbable specimen at the very moment our technological eyes opened wide enough to see it? These technological advances are redefining the boundaries of detectability, pulling objects out of the darkness that would have remained invisible to earlier generations of surveys. What looks like the sudden arrival of massive interstellar visitors may instead be the result of our sharpened gaze, the product of instruments that can now capture faint signatures that were always there, drifting silently, but hidden beyond the reach of our former capabilities. At the same time, the evolution of survey strategy has transformed how the sky is monitored. Improved cadence patterns, smarter data processing algorithms, and increased coordination between complementary facilities have all optimized discovery rates. Modern surveys balance sky coverage with repeat observation frequencies, ensuring that transient phenomena, from supernovae to near-Earth asteroids to elusive interstellar wanderers, are not missed in the gaps between observations. Standing at the peak of this revolution is the Vera C. Rubin Observatory. Its legacy survey of space and time embodies the culmination of these technological and strategic leaps, a facility designed not just to expand our vision, but to systematically reveal what has always been there, waiting to be seen. In the end, Atlas continued its silent journey, past the orbit of Jupiter, then Saturn, fading slowly into the black from which it came. Its visit was brief, almost imperceptible in the scale of cosmic time, but for us, it was a revelation. It reminded us that the universe is not a static map, but a living ocean, vast, unpredictable, and filled with travelers from distant shores. Oumuamua, Borisov, Atlas, 3 messengers, each one stranger than the last. Each one whispering the same truth. We are not alone in the galactic void, only unaware. Atlas's trail may have vanished from our skies, but its legacy burns brighter than ever in the minds of those who watched it pass. It challenged our assumptions, our technology, even our imagination. It forced us to look outward, deeper, further. And that is where the story truly begins. Because somewhere out there, beyond Neptune, beyond the reach of our telescopes, countless other wanderers are crossing the darkness. Some small, some vast, some carrying secrets older than our Sunday. And one day, one of them will come close again. When it does, we must be ready to detect it sooner, to study it closer, to meet it not as startled observers, but as explorers. Atlas reminded us of our greatest gift, curiosity, the drive to seek, to understand, to keep looking into the unknown. So let it be our call to action, not to fear the vastness, but to embrace it, to build the instruments, the missions, the eyes that will pierce the dark, because the next messenger is already on its way. And when it arrives, the universe will ask us once again the oldest question of all. Are you ready to see what's out there?